Okay. Remember, if you got your general first order differential equation, whether it's linear or not, whether you can solve it using the methods that we're saying or not, if this is a continuous function, then we can start at any point we like. And y prime, if we plug in the values of x and y, we're going to get a value that's equal to y prime, which is the slope of a solution curve. So we follow the slope of the solution curve. So here's our point. X naught, Y naught. And here is the segment slope f of x naught, y naught. And we know that a solution curve through this point has to be tangent to this segment at this point. Now it might diverge, it probably will. But if the length of this segment is small enough, it won't diverge much, in the sense that any divergence will be a very small percent of the distance that we travel, okay? The other thing is, typically, and I haven't actually checked your book. I mean, I glanced through the section some time ago. I don't remember them using a letter other than H, although we can use delta X if we want for this displacement, okay? And this is going to be the same for every segment that we draw. Well, we draw this segment and we get out to this point, which is going to be x1, y1. And of course, x1, y1, well, this is h or delta x. How far do we go here? And let's draw this out here because I don't want to clutter up the picture a whole lot more than I already have. I'll use delta x here. Okay. Well, delta y over delta x is a slope, so delta y is a slope times delta x, which equals, of course, f of x naught, y naught times delta x. Coordinates at this point are x naught, y naught. So the coordinates at this point are x naught plus delta x y naught plus delta y. And delta y is this. Okay. And now we're going to call that x1, y1, because we're going to be able to compute that. Now you're going to compute it by hand for several examples, but then the web assigned homework ask you to do some comparison with what computer algebra systems give you. And whatever system you have, it's easy to set up the process once you see what the process is. And you've already kind of seen it because we did it probably in the first day. So anyhow, by this, you get x1, y1. And then what are you going to do? You're going to go over another h units. And generally, we use the same increment here that we use here. And I went too far. There's no reason to do that. Okay, so here we have it. And we get a point x2, y2. How do we get this point? Well, we get this point by doing the same thing with x1, y1 that we did with x0, y0. So this triangle gives us a delta x and a delta y. Just to be complete, I'll say slope here is f of x naught, y naught. On this one, well, this point is x1, y1. The slope is f of x1, y1. So now we conclude, and I'm not going to write out all the details, that coordinates at this point are going to be, well, we're going to call it x2, y2. And that's going to be x1 plus delta x. Y2 is going to be y1 plus the new delta y. And of course, the delta y is going to be, again, slope times run, or f of x1, y1 times delta x. So there we have it. Okay, really simple. Do you agree?
Seems simple enough.
Well, now we do a whole lot of unnecessary stuff. We write out formulas and stuff. Common sense tells you exactly what you need to do. But your book is going to write out a bunch of formulas because your book has to assume that some people need them. I don't think you do, but let's just make sure we understand what those formulas are telling us. I'm quite sure that I could now turn you loose with any function here that you can evaluate, and you can take this step as many steps as you want. If I just tell you what the coordinates at this point are and what to use for your delta x. Okay. So in general, you're going to kind of make a table to see how everything develops. word's a little warped. Is it a reason for that? Yeah, don't worry about it. So again, okay, we're going to make a table. We're going to have X here. We're going to have Y here. We might as well have delta X, which is going to be the same every time. We're going to have f of x, y. We're going to have delta y. X is going to be x naught. Y is going to be y naught. Debating about something, but okay, we have a delta x here. And just for a little variety, I'm going to call this h. And in every step, delta x is going to be h. And we have f of x, y. Well, that's going to be f of x naught, y naught. And then our delta y is going to be okay. And then let's go ahead and put our new x, not necessarily do all this, but we'll do a little overkill. Let's write our new x and our new y. Okay, our new x is going to be x plus h. And that's going to be x1. Our new y is going to be that could be x naught plus delta x. Y naught we use h. I don't know if you can read that. Y naught plus f of x naught, y naught h. I was originally planning to do those two. And this is going to be our y1. Okay, there's our calculation. So now x becomes x1, y becomes y1, and this becomes f of x1, y1. This becomes f of x1, y1, delta x. This becomes x1 plus h, which we call x2. And this is going to be y naught plus f of x1, y1, h, which is going to be y2. And it's not y naught, it's y1. Now it's going to get kind of monotonous. I'll write out one more step, and then I'll probably skip. You know, I've written h instead of delta x here, but I've been writing delta x over here. And I really ought to write just h. And then over here, since I didn't have room, I have to use this extra space I got. Leave myself some space. Y2 plus f of x2 y2h, and that's equal to y3. So that now I have x3, y3, and I can write it all out again. But really what I want to do is I just want to put some dots here. So eventually I'm going to have, well, actually in every step I have x n minus 1 and y n minus 1. Still going to have h. Going to have f of x n minus 1, y of y n minus 1. And I'm going to have f of x n minus 1, y n minus 1 times h. I'm going to have x n minus 1 plus h. And that's going to equal what? Well, it's going to equal x sub n. Because, of course, every time the subscript of x increases by 1. Okay. And if I increase n minus 1 by 1, that's a subscript. It increases by 1, it gives me n. And that's pretty obvious, but we want to make sure we say it. And then we have y n minus 1 plus x of x n minus 1, y n minus 1, h, and the h is kind of squeezed in there, and that equals y sub n. So now I have x sub n, y sub n, I've still got h here. And this can be extended as far as we want. And right here is a formula for the nth step. Okay, and the formula consists mainly just of this, which is obvious, and this. Those are the essential parts of the formula. So we have a shorthand notation. Which just says x sub n equals x sub n minus 1 plus h, and y sub n equals y sub n minus 1 plus f of x sub n minus 1 y sub n minus 1 times h. And all the rest of this is just single step-by-step application of what we say here. And also shorthand notation for the whole thing. Well, in other words, to apply this, we need the function f of xy. It has to be something we can calculate, and we have to have a starting point. Well, that's the method. And writing all this out, I think is fairly unnecessary, but use as much of it as you need to. But just understanding the shorthand notation tells us to do this, so we just go ahead and do it. So let's do a specific example. And I'm going to pause the video for just a second. Okay, do an example now. Here's a function f of x, y. We notice that it's not defined when x equals 0. So we can't extend a solution across the y-axis, looking at it geometrically. If I give you a solution that starts at -2, 3, that solution is going to work up until you get to the y-axis. Now, when I say it's going to work, it's only an approximate solution, because remember, in every interval, the function's not actually straight. Okay, this function though can be straight in much of any interval. So on every interval, you have a slight deviation from the accurate solution. And one thing we want to do is be able to explore what happens if we shrink the value of h. Okay, well, here we have it. Okay, so let f of x naught y naught equals 0.5 equals one f of x y naught, and I was about to write my increment, and I realized that what I was writing made no sense. Okay. Let's let x naught y naught equal to 0.11, and h, or delta x, whichever you want to call it, equals 0.5. So I'm going to abbreviate the table a little bit. I know that if I've got x and y, I can calculate f of x, y, and that's my slope. So that I can do all of this. And I'm going to just throw in another column here for n, the number of my step. Okay, so n equals 0, then x equals x naught, y naught. That's 1. Well, okay, x equals x naught, y equals y naught, 1, 1. So f of x, y equals what? Well, very easy, 1 over 1 is 1. So f of x, y is 1. So delta y is equal to what? Well, delta y is equal to f of x, y times delta x, or times h. So
Would
this, I'm sorry, go ahead.
wouldn't f of x, y be equal to 2? Because it's x squared plus y over x.
Yep. Don't ask me. Okay, so delta y is going to be, and then thank you, because it wouldn't have been good. Okay, this is 2 times 0.5 equals 1. Okay, I was already thinking ahead to that. I'm not making excuses. There's no excuse. Okay, so 2 times 0.5 is 1. Okay, so your new x is going to be your old x plus your delta x, which I haven't even written here, but wouldn't necessarily be a bad idea. So I could just look at this column and that column and add the 2. And that's a step you want when you set this up using whatever software. Okay, so 2.5, 2 times 0.5 is 1. Your new x is going to be 1.5. And your new value of y is going to be 1 plus 1 and that's 2. Okay, again, you're at the point 1, 1, and you're going up with a slope of 2, and you're moving over half a unit. So you're going up 1 unit. Y started at 1, you add the change, and you get 2. So now n is 1, x is 1.5, and y is 2. So what's f of xy? Let me do this one right. You square 1.5, you get 2 1/4, 2.25. And then you do y over x, which is 2 over 1.5. That's 1 1/3, like 1.33. But you're adding 2 1/4 to 1 1/3. Okay, you do that with fractions. Of course, you're going to use software to do it. But 2 1/4 is 9/4, and you're adding 4/3. You got to go to this common denominator of 12, and you have 27 and 16, 45 twelfths. Okay, I think. So f of xy, if I did it right in my head, is 45 twelfths, which is just short of 3. It's 1/4 short of 4. So that's a little weird that it should come out that even, so I won't guarantee it. But so let's say 2.75. Okay. That can't be right because you're adding 2 1/4 to.
I think it's 43 twelfths.
It's 3.75. I'm sorry, did you get it? What?
Oh, never mind.
Yeah, okay. Working memory.
Yeah.
Ain't what it used to be. Okay. Fortunately, I've had no physical deterioration over the years, so I'm happy. Okay. 3.75. Okay. Let's just pretend that's right. Maybe it's right, maybe it's wrong. But anyhow, your delta y is then going to be leave myself a lot of room, but that's going to be 1.875. Yeah, I think that's right. So we'll pretend it is anyway. And then my new value of x is going to be 1.5 plus 1.875. And that's going to be 3.375, 3 3/8. And if I keep my mind on what I'm actually doing, that's the kind of thing I'm going to get over here. It's going to be my x value plus 0.5. That's going to be 2. Mixing up 2 calculations because I'm thinking ahead again, or thinking without my head, I don't know. Plus 0.5 equals 2. And then this is going to be 2 plus 3.75. And that's going to equal 5.75. So in the next step, we're going to have n equals 2, x equals 2, y equals 5.75. So this slope is increasing pretty rapidly. Now we could do another step, but it would be just like the previous steps. Maybe I can do an estimate. 2 squared is 4, 5.75. And just estimating, that's going to be about 33. And 33 over 2 is about 16 or 17. So maybe 16. This is going to be then approximately 16 times 0.5, which is 8. So your new x is going to be 2 plus 0.5, which is 2.5. Your new y is going to be 13.75, and everything's just kind of an et cetera. We're going to have 0.3, going to be 2.5, approximately 13.75, and so forth. Okay, now it's totally mechanical. This thing has a rapidly changing slope, obviously, as we move to the right. Y is going to keep increasing, and x is going to keep increasing, but y is going to turn out to increase faster because the x squared and the ratio and all that stuff. We do the same problem with h equals 0.1. Okay, so I'm going to just kind of continue the columns. Okay, so at 0, everything's going to be the same until I calculate my delta y. And now I got h equals 0.1, so I'm going to multiply 2 by 0.1. Okay, and that's going to be 0.2. And then my new x will be 1.1. My new y will be 1.2. So now at 1, I'm going to have x equals 1.1. And my x's are going to go 1.1, 1.2, 1.3, 1.4, 1.5. Okay. 1.1 squared is 1.21. Actually, let me get my y value in here. It's 1.2. Okay. So I'm going to get a 1.21 here, and I'm going to get 1.2 over 1.1, which is pretty close to 1.1. So I'm going to fudge it a little bit. Probably fudge a little bit within that. But my f of xy is then going to be 1.1 plus something little shy of 1.1. I'm going to round that off to 1.19. And it's already an approximation. 2.19, got to add the ones. Okay, and then here I'm going to get my delta y is going to be 2.19 times 0.1 equals 0.219. And my x is going to be 1.2. And over here, then I'm going to have 1.2 plus 0.219 equals 1.419. Okay, then I'm at 0.2 and I've got 1.419. 1.2 squared is 1.44. 1.419 over 1.2 is, again, pretty close to 1.2, but a little less. So I'm going to get something about 2.419 1.41. Over here, I'm not going to write out the multiplication now. I'm going to get multiplied by 0.1, so it's pretty easy to do that multiplication. And I'm going to get 1.3 for the x. I'm going to get 1.2 plus 0.241 equals 1.66. That's 3. Now I've got 1.66. 1.3 squared is 1.69. So 1.66 divided by 1.3 is just less than 1.3. I add that to 1.3. And I get something a little less than 2.6. I don't know, 2.58 might be it. So I'm going to get a 0.258 here, and I'm going to get a 1.4 here, and I'm going to get a 1.3, a 1.66. Uh-oh. Well, I screwed up. I added this to 1.2. I should add it to 1.419. But that's apparently what I did. I wrote down 1.2, but I added 1.419. So, okay, so this is going to be my y, which is 1.66. Into that, I add my delta y, which is 0.258. And that's going to give me like 1.914. Maybe. I'm not going to check it. It's acting about like it should. Now, remember, we're going to end up with a value at 1.5. The value that we got here was 2. It's pretty clear from this pattern that I'm going to go pretty well over 2. So that what I had here was an underestimate. Now that's consistent with the fact that the slopes are pretty rapidly increasing, so that when I make this straight line approximation, I'm not really getting a really good approximation to the curve. Well, we're close, so I'm going to go ahead and work or fudge the rest of this. Actually, these calculations are pretty easy. There's 1.4 squared is 1.96. So I see that this result is going to be at 1.4 squared, which is like 1.96, added to y over x, and y over x is a little less than 1.4. So I'm going to get like another 1.96, but maybe 1.93, which is going to give me like 3. That's a pretty big jump. But remember, we're squaring this number, and squares increase faster and faster. And the y is exceeding the x by more. We're not going to square it both times. Okay, it's going to be like a 1.96 plus a 1.4. Would give me 2.36, but probably a little less. I'm going to guess there's 3.36, 3.32. So it'd be at 0.332. We're going to get 1.5 here, and we're going to get the previous value of y, which was 1.66. No, that was there. It's 1.914 plus 0.332, and that's going to be approximately 1.2 46, but I'll say 2.25. I keep being careless with that, but it doesn't make sense, so it's easy to find when you do it. So we're going to have 2.25 here. So here's my 2.25. 1.5 squared is 2.25. 2.25 divided by 1.5 is 1.5. So that x squared plus y over x is going to be 2 1/4 plus 1.5, which is 3.75, giving us 0.375. So now our next x is going to be 1.6, but that's going to be in the next step. And here we're going to have then this plus this, and that's going to be 2.6275, so about 1.63, 2.63. Okay, so we get about 2.63. Now, the point of that whole mess is that when x is 1.5, this predicts a y value of 2. Over there, that wasn't right. Okay, when x is 1.5, y is 2, that's obvious. This indicates that when x is 1.5, y is, mess it up completely, y is 2.63. Okay, why did this end up bigger than this? Because we're using a shorter interval instead of saying that over an interval of 0.5 units, which is pretty big compared to the 0.1 units, that the slope stays the same. Here, we're allowing the slope to keep adjusting. So I can draw a picture of that. Let me see what I would have used to draw the picture. Okay, so our first approximation looks something like this. We got this point, and we got a slope, and we've got this point. Now, this point was 1, 1. This point is come on now. This board's a little rough, so I'm going to correct that. Okay. The same approximation here. Now, if I draw this dotted line out here to 1.52, I can now compare what happens. I can break this interval into 5 subintervals on the x-axis. And on this first interval, so here's 0, here's 1, here's 1.5. On this first interval, what slope did we get? We calculated a slope of 2.19. Sorry, we used a slope of 2. Okay, so in the first interval, the slope we got for the fine approximation is the same as the slope we used up here. So here, slope is 2. On the next interval, I think the slope is 2.19. Yep. On the next interval, the slope is 2.19. So we diverge from this line. And on the next interval, the slope increases to 2.41, which makes it even steeper than it was here. Not sure I drew it that way. And on the next interval, it increases more to, what was it, 2.7 or something like that? No, just 2.58. Not sure I got that one right, but let's see. And on the last interval, slope went all the way up to, 3.32, and something's wrong. Oh, well, not going to worry about that. Should worry about that because they think hit me in the knee. Okay, not very hard, but it hurt a little bit. And then the slope is, whether this is accurate or not, that's not 3.32. Well, that's what we got. So something's wrong with my arithmetic, but that's to be expected. You do the arithmetic accurately. The point is that this thing is curving upward rapidly, and that's consistent with the way this thing changes. The curve here went up to a slope of 3.75 for the next interval. So it's clear that the slope appears to be increasing. And if you look at this function and analyze it a little bit, you can see why. This thing fell in the bucket, which knocked the squeegee off. Wouldn't pick a squeegee up. Okay, next slope. Also show off that I can still lean over. Next slope is this. Well, each of these slopes increases. I don't think I have the numbers completely right. But the whole concept of increasing slopes, every slope did increase. I think they increased a little more smoothly than I'd indicated though. So that we have now this discrepancy. And this arrow represents a correction using increment 0.1 rather than 0.5. That accommodates the actual changes in the slope. Okay. Another important point is that the upward curvature implies that every slope averages a greater value than the value used on each interval. So every approximation is an underestimate. Meaning that the actual curve lies above any curve that we predict. If I did another approximation using a much smaller slope, like, okay, we made the slope 5 times smaller here. We're going to make it 10 times smaller. Use 0.01 because it's really convenient to use, 0.01, 0.001 and stuff. We'd have had a correction, but that correction would have been smaller than this correction. So the actual slope, the actual curve, I'm going to stick my neck out. I'm not going to have room to write this. Actual curve is closer to the second approximation. The second approximation is to the first. Okay. Those are important ideas. How does refining your increment refine your prediction? If I used an increment of 0.01, I would have 50 increments here. I know, or at least I'm pretty confident, if I analyze this function and see how it behaves in two-dimensional space, which I can do because we know multivariable calculus, I can actually prove that the slopes are always going to be greater on the next approximation, on a smaller approximation than they are on the one we use. I could do that, but I don't think, if the approximation here is this big, just my intuition, which is fairly good, but not totally reliable, I think the next approximation will probably show a discrepancy on the order of 1/10 of this one. Not just because I'm using 1/10 in 100th, but I suspect that you can run this stuff. You run it very easily on Excel or using computer algebra system. And I'm going to run it in Excel here in a minute, provided I can share my screen. Now, another thing is, of course, we can test what I've said here because it's easy to solve that equation and plot the curve. Okay, it's a simple first order, non-homogeneous linear equation. You're going to have an integrating factor that's natural log of x. Multiply both sides by that, do the solution, rearrange it, solve for y, and you get a curve here which is going to have some an exponential characteristic. Okay, I haven't solved it, but if you look at it and think about it, and think about what I just said, you'll probably see that much. If you work it out, you'll see that I was either right or wrong, so it's worth working out. So I think the ideal curve, and this is a fair depiction of what actually happens, the ideal curve is going to be almost identical to this, and then it's going to diverge just a little. So here's your ideal curve. You get that by solving the equation. So what's the use of the method if you get the ideal curve by solving the equation? Well, one use is even if you can solve the equation, you get more insight into how the slopes are changing between 2 points. And you get some insight into how the analysis of this function of 2 variables can give us important information. Okay, in the nature of this thing, you can think of the surface that represents the curve of this, or this function of 2 variables in 3 dimensions. And then you can think about where you are in the plane down below that curve, look up at the curve and see in the neighborhood of that point how the slopes are changing as you move in various directions. And especially how they're changing if you move in the x direction. Now, they don't expect you to digest that, but you can do all that. And it's worth doing because, especially because there are plenty of functions here that I could write down that it's impossible to solve the differential equation for. And then we're stuck with approximations, and we have to know how approximations behave. So the point of this section is not so much, here's how to do the method. The point of the section is what this method tells you about functions and about the accuracy of your approximations. That's where the real meat of the Euler method is. Okay, well, I'm going to set up the Excel and show you how quickly this can be done. Just quickly, we didn't pick up the Excel, so I'll have to do that in a supplement. But it showed that my explanation here might have had something wrong with it because the predictions we get out here actually go down. And I was actually wrong that the discrepancy between here and here gets greater if we go down to increment of 0.1. We have a greater discrepancy between here and here. So the actual curve will be further than this from the original. And Excel's saying it's going to go down. I don't have a good explanation for that, but I'm going to think about it. Maybe do a little supplemental video. Okay. Anyhow, there we have it. So my wife and I are going to get vaccinated today. So if I'm still alive on Tuesday, we'll have class. And I'm not the least worried about it. So any questions, comments? Okay, I share the screen. And when I shared the screen before, we didn't get the shared, I didn't hit the record first. So I'm going to see if this works. I know the sharing is going to work. We'll see if it switches over. There we go. And we want to get the Excel screen. And here it is. Okay, well, here's a curve I got from Excel, but let's put that off to the side because that comes up a little later. I'm going to assume some familiarity with Excel. I've set up the same table, n, x, y, f of x, y, delta x, delta y, new x, new y, exactly as I've set up other tables. Although the last set of tables I set up, I didn't include the delta x, but on earlier ones I did. Now over here, I've got the value of h, which we started out with as 0.5. And before I change that, I'm going to make sure that we don't have too much stuff here. So I'm just going to do 10 steps. And everybody should be familiar enough with Excel that you know what I'm doing. And I should be able to delete that. And I hit the delete key. Well, no, I didn't. I hit the insert key. Okay. Now, we started out with h equals 0.5. X naught was 1. Y naught was 1. And this calculation is just done by cell reference. X naught is the D2, which is where X naught is. It's here. And I've got dollar signs in front of the D and the 2 so that this cell reference doesn't change. So that, well, that's my initial X value. My initial Y value is here in F2, and that's equal to F2 with the dollar signs. Okay, then f of xy is my function, which is my x squared, in this case d4 squared, plus y over x, e4 over d4. That's this. Why should that be e4 over d4? That's probably one of my corrections. Okay, so seems to me that this should be f4 over d4. And that's not right. This should equal this. Oh, never mind. It's right. It's this over this. So I was going to the fixed cells, and that wasn't a good thing to do. Okay. In any case, these three lines mimic what I got on the board. And what I got on the board was an estimate of 5.75. So I'm going to say my board in the brain, we compare that with 5.75. Okay. Now, if I want to look at the approximation of, let's just say, the y value when x equals 2, the prediction was that the y value for x equals 2 would be 2. And that clearly isn't right. Never mind, I'm looking at the wrong columns. Okay. And we're getting 3.125, so that should actually be this comparison, and I'm losing track. Something is wrong in this step because the delta y should equal my f of xy. The f of xy, okay. I changed my formula here and forgot to add my x squared, which is this. Okay, so now we have it. And now this tells me Okay, I see what I did on the board. Anyhow, okay, so we have a scheme here. Same scheme I followed, but I made a kind of a big boo-boo on my first step. This is what I ideally should have gotten when I got to 5.75 on the board. Okay, now that's not the point. The calculations are set up exactly as they were on the board. If I change H, we do one more thing. If I change H to 0.1, well, that changes a lot of things. And I see that now when X equals 2, I get 5.34. And when X equals 1.5, I get 2.33. Now, when I did it on the board, I got 2.63 here. And I'm not sure what I did wrong, but you want to look at what I did. And I'm not going to make all these comparisons. I can't point to the board and everything. But we see that now I get predictions for X equals 1.5, Y equals about 2.7, well, about 2.33. When X equals 2, Y is about 4.71. Using 0.1. If I want to change my increment to 0.01, and then want to see what happens when X equals 1.5, well, I've got to take all this and drag it down. And now I see that when X is 1.5, I get 2.42. Now the 2.42, you can ignore these comparisons because they're not going to make as much sense. And unfortunately, I can't quickly go back and forth. Okay. At 1.5, we get 2.42. You can compare that with what we got at 1.5 before and see which way these refinements are moving our estimates. Okay, so there's the process. I was a lot more coherent when I did it in class, and I've got to quit now. So the whole process comes down to setting up your H here, your X naught here, your Y naught here, and then doing everything by cell reference. To review that, X is equal to $D $2, which is going to be this value here. When n equals 0, so that's going to be your X naught, and your Y naught is going to be $F $2, which is this. Your f of xy, which is x squared plus y over x, now has d4 squared. Well, d4 is here, that's your x value. And then plus y over x, your y value is e4, your x value is d4. So that this gives you your y over x. This is your x squared. And your delta x is your B2. Okay. Once we've got that, we go ahead and calculate delta y, your new x, your new y, new x, new y here. Then we drag all this down. To get this second row, which just changed for no reason I can fathom. And then we drag all this down as far, well, we can't do that. We've got to drag all these rows down, and the numbers changed. So I did something wrong, but you know. Let's see what I do wrong. Okay, yeah, I can't drag all that stuff down. No. Okay, drag all this stuff down. Then if I can hit the corner, we drag this stuff down and it's still not right. Why not? It's because I dragged down the wrong columns. Well, you can work with the Excel and do that. It's very easy to set this up. It was set up correctly originally. Going back inside of this, things got a little screwed up. What should have been dragged is these two lines. And that doesn't work. I have to set it up from the beginning. Okay, anyhow, there's the Excel.